Hello, calculus fans. We're now going to talk about partial derivatives. This is a key concept in multivariable calculus. In one-variable calculus, we talked a lot about rates of change of functions. We developed a derivative, and we did that using average rates of change, and then we moved along to instantaneous rates of change. And we ended up defining the derivative of a function of one variable. And if you'll recall, the derivative was defined to be the limit as h approaches 0 of f of x plus h minus f of x all over h, provided that the limit exists. We had a very wide variety of applications of the derivative. Let's now extend this idea of derivatives to functions of more than one variable. So as an example, let's talk about something called the heat index. The heat index gives you a measurement of how hot things really feel based on the temperature and the humidity. When it's very humid, it feels much hotter than it actually is. And when the air is dry, it feels cooler than it actually is. We'll use I for the heat index, T for the temperature, and H for humidity. So I is a function of T and H. So we'll write I equals f of TH. And I'd like to show you a table of values of the heat index that's compiled by the National Weather Service. Here's the heat index table from the National Weather Service. So the way you read this is you look up the actual temperature T and the humidity, and then it tells you what it really feels like outside. So when the temperature is 90 degrees and the humidity is 65%, then it feels like it's 108. Whew, that's hot. All right, it may be useful for you to have that table handy. Let's focus on the highlighted column of the table. That corresponds to when the humidity is 70%. So we're thinking of the heat index as a function of a single variable T for a fixed value of H. We'll write G of T equals f of T 70. So we're fixing the humidity to be 70. This function describes how the heat index changes as the actual temperature changes when the humidity is fixed at 70%. So the derivative of G when T is equal to 96 degrees Fahrenheit is the rate of change of the heat index with respect to T when T is equal to 96. So we can write it like this. G prime of 96 is equal to the limit as h goes to 0 of G of 96 plus h minus G of 96 all over h. Now translating it back into the heat index function, that's a limit as h goes to 0 of f of 96 plus h comma 70 minus f of 96 comma 70 all over h. Let's try to approximate G prime of 96 using the values in the heat index table, and we'll choose h equals 2 and then we'll choose h equals negative 2. So for instance, if we choose h equals 2, then we can say that G prime of 96 is approximately equal to G of 98 minus G of 96 all over 2. It's not a limit right now. We're actually plugging in a small value of h to estimate the derivative. The smallest value of h that we can use in this case is 2 because that's how the temperature increments. If we plug all this into the function f, we end up getting 4. Now we could also approximate it using h equals negative 2. When we do that, we end up seeing that G prime of 96 is equal to G of 94 minus G of 96 all over negative 2. Work that out, and we get 3.5. Now we can get a reasonable estimate for G prime of 96. We'll just average these two answers that we got, 4 and 3.5. Those average out to 3.75. Now here's the important thing. We would like a real-life interpretation of this number. What it's telling us is that the heat index is rising about 3.75 degrees for every 1 degree increase in temperature when the temperature is 96 degrees Fahrenheit and the humidity is 70%. So just a 1 degree increase in the temperature means the heat index will go up about 3.75 degrees. Now let's look at the highlighted row in the table. This is going to correspond to a fixed temperature of T equals 96 degrees Fahrenheit. So the temperature now is not changing, but now we're going to allow the humidity to change. So the numbers in this row are values of the function big G of H is equal to f of 96H. That describes how the heat index will change when the actual temperature is 96 degrees Fahrenheit. So if we differentiate this function when H is equal to 70, it's the rate of change of the heat index with respect to humidity when the humidity is 70%. So we could say that big G prime of 70 is equal to the limit as H goes to 0 of big G of 70 plus H minus big G of 70 all over H. And that's the limit as H goes to 0 of f of 96, comma, 70 plus H minus f of 96, 70, all over H. And again, we're going to go ahead and approximate the value of G prime of 70 using the values in the heat index table. Now we'll take little h equals 5 and little h equals negative 5. Those are the smallest increments of humidity that we can use. So to estimate G prime of 70, now we'll plug in h equals 5. Notice that this is no longer a limit. We're estimating the value of G prime of 70. So it's G of 75 minus G of 70 all over 5. Plug that into the f function, work all that out, and we get 1. Now we can do the same thing, but instead of using little h equals positive 5, we'll use little h equals negative 5. So G prime of 70 is approximately equal to big G of 65 minus big G of 70 all over negative 5. Plug all that in, and we end up with 0.8. And once again, in the same manner, we'll average the last two values, and we end up with G prime of 70 is approximately equal to 0.9. And again, here's the important thing. We want a real-life interpretation of this number. This is telling us that the heat index is changing about 0.9 degrees for every 1% increase in humidity when the temperature is 96 degrees Fahrenheit and the humidity is 70%. So increases of 1 unit of temperature makes a big difference in the heat index. Increases in the humidity, not so much. In general, what we'll do is we'll start with a function of two variables. Those variables will be x and y. And if we only let x vary and we keep y fixed, let's say y equals b, then we have a function of only one variable. That function will be g of x equals f of x comma b. If that function has a derivative with respect to a, then we call it the partial derivative of f with respect to x at the point a, b. And the way we'll write it is with f sub x of a comma b. So we can say that f sub x of a comma b is equal to g prime of a, where g of x is the function of one variable defined by f of x comma b. Now if we use the definition of the derivative, we know that g prime of a is equal to the limit as h goes to 0 of g of a plus h minus g of a all over h. And from that, we get this expression, that the partial derivative of f with respect to x at a, b is equal to the limit as h goes to 0 of f of x plus a, b minus f of a, b all over h. And we can define, in a similar way, the partial derivative of f with respect to y at the point AB. It's going to be denoted by f sub y of AB. This time we keep x fixed, and we find the ordinary derivative at b of the function g of y equals f of a comma y. So, the partial derivative of f with respect to y at the point AB is now the limit as h goes to 0 of f of a comma b plus h minus f of a comma b all over h. If we go back to the heat index problem, we can use our notation to write down the rates of change of the heat index with respect to the temperature and relative humidity. We estimated that the partial derivative of the heat index with respect to temperature at 96 and 70 is about 3.75, and the partial derivative with respect to h at 96, 70 is about 0.9. The next thing we'll do is we'll let the point a comma b vary so that f sub x and f sub y become functions of two variables. And we'll finish up by making a definition to say that if we have a function of two variables, we'll say that its partial derivatives are the functions fx and fy defined by these limits. In the first limit, the plus h goes into the x component. In the second limit, it goes in the y component. And of course, that's provided that these limits exist. Okay, that's all for now.